final talk by Kengo Nakajima, the efficient parallel multigrid method on the Intel Xeon Phi clusters. Okay.
So can you see the slide?
Yes.
Okay. Thank you very much for introduction. So my talk is on the efficient parallel multigrid solver on Intel Xeon Phi cluster. So just a moment. So this is a joint work with my colleagues from RIKEN and Intel. So first, I'd like to make acknowledgement to my sponsors and also the confidential resources. So I believe most of you are familiar with the multigrid method. It's a scalable multi-level method for solving linear equations. So it's a so-called order n very scalable algorithm, and it's expected to the very nice tools for the exa-scale computing. But so we have many problems, okay, to be solved. So this is an overview of our target applications. It's called PGW3D FEM. It's a 3D groundwater flow via heterogeneous porous media like this way. So using the Finite-Volume method on the structured cubic voxel mesh. So we are solving the Poisson equations with this lambda. It's so water conductivity. So it's randomly distributed. And so we have a little bit ill-conditioned so storage matrix. So because it's a SPD symmetric positive definite, we can apply the conjugate gradient solvers. So we are now applying the conjugate gradient method preconditioned by multigrid. So it's called MGCG. So we are applying the octary-based geometric multigrid and incomplete choice key 0 without filling, smoother, recycle, and artificial domain decompositions. So actually, so this is a very memory-bound process, and so matrix storage affects the performance so much. So we start this from the CRS, and in the previous version, so we are using this sliced ELL. So this is my old result using Fujitsu's Prime HPC FXN. It's a commercial version of the K computer. It's a very old result. So this is a result up to the 4,000 nodes by 65,000 cores. And so this is a result by the CRS weak scaling, and this is a result. So this blue triangle. So it's a sliced ELL plus CGA. You can see we have almost twice improvement of the performance. So as I mentioned, so MGCG is a sparse linear solver. So this is a typical memory bound procedure. So effects of the memory access or matrix storage are very significant. So you can see this effect. So this is a slide which I presented last year in this workshop. So that at that time I just measure the scalability with our solvers on Oakforest-PACS by night running and OBCX with a cascade rate. And this is the last slide, which I showed last year. And so I mentioned some future works, and among that, I showed the cell C sigma, for the new type of the matrix storage method. And so I promised to implement it. So this one to our solvers, and this year I would like to show our result using this cell C sigma. And I believe most of you are also familiar with the cell C sigma. It's a very well known, and it's very suitable for modern multi-core, many-core CPUs or GPUs with wide SIMD. Okay, so it's proposed by Gerhard Wehring group just several years ago. So this is the idea. So we are extracting the small length vector, 8 or 16 according to the SIMD size, and apply the local vector computing. So purpose of the present work is applying Celsius sigma to the MGC solvers in this application. So currently, so it is based on the sliced ELL. So it's more flexible than ELL, but so yeah, we are switching to the more efficient method. And the sliced ELL and Celsius sigma have been mostly applied to the sparse matrix vector multiplication or Gauss-Seidel iterative solvers were smoother. So actually, implementation to the forward and backward substitutions in ILU-type smoother is very difficult in the sliced ELL and Celsius sigma. And I think that my result in 7 years ago, 6 years ago was the first example of the sliced ELL in such case. And so I believe this work is the first example of the Celsius sigma to this type of the forward and backward substitution. So this is the overview of the present work. So we are applying the weak scaling, using this type of the coarse grid aggregation with a single level, and using an Oakforest-PACS using up to the 1024 nodes. And it's a flat mode and MCD only. And we have a 68 cores on each node, but we just use a 64 cores. And the flat MPI and hybrid 2x32. 2x32 means the 2 threads and 32 MPI processes on each node, and 4x16 and 8x8. And so this is the problem size, and so maximum problem size is 4.29 billions of degrees of freedom. And I measured 5 times and so adopted the best one. And we also evaluated the MC kernel. So basically, we compare the CRS sliced ELL and Celsius sigma SCS. And in this study, we fix the value of the C and sigma as 8. Okay? And so if the problem size is small enough for each color and thread, so less than C, so we switch to the original sliced ELL. And also as a distant coarse grid solver, so we just apply the sliced ELL, not the SCS. So we are expecting a 20% improvement on the SCS solver over sliced ELL based on the preliminary result. So this is our target system, Oakforest-PACS. So it's an Intel Xeon Phi night running with a omnipath architecture. So it's made by Fujitsu. So we have more than 8,000 nodes, and it's 22nd in the most recent top 500. So I believe this is the second largest night running system in Asia. Okay? So it's operated by JCAHPC. It's a joint work between University of Tsukuba and University of Tokyo. So yeah, this system is widely used for a variety of the applications. Okay, so next slide shows that MC kernel. Here I don't get into the detail, but so this is a lightweight multi kernel OS for HPC developed by RIKEN by Dr. Ishikawa and Balazs. So it provides a lower noise and a lower communication overhead than pure Linux and environment, so very easy to use. So this is a effect of the only Linux case and MC kernel case. So yeah, we achieved a significant improvement of the MGCG solver by 20% of the Oakforest-PACS with 131,000 cores. So this is corresponding to 2,048 nodes. So we presented in SC19 workshop. Okay? So here we are also applying this MC kernel in this work. So this is the 3 types of the implementations for the sliced ELL. So this is the original code, and the 2 types of the Celsius sigma. So type A is a row-wise. Row-wise means that we are doing this type of the computation in row-wise. Okay, so the innermost loop is a column-wise, and the SCS-b is a column-wise loops, and so yeah, it's a very typical loops for the vector computation. So you can see, so if you compare the SCS-A and SCS-b, so this one is more expensive because we need some copies before and after the main computation. But generally speaking, so this one is more suitable for the real simile type computation, is more efficient. And we also adopted the coarse type ordering using CM-RCM2 type coloring. Okay. So I don't get into the detail of this slide, and so this is a red black, and so it's a very famous one. And on the contrast, so CM-RCM2 is also two colors, red and black, but so numbering is a little bit different. And we first apply the reverse Nakajima, and then apply the cyclic multi-coloring for each level of the reverse Nakajima. So this one is more efficient, and so yeah, so that's why we adopted CM-RCM2. So this is the result. So time for MGCG. So using 8 nodes and hybrid 4x16. So this is the time. So elapsed time for the MGCG, and down is good. Okay. So CRS, sliced ELL, and so 2 types for the Celsius sigma. Okay. So here, so level 1 to level 4 means that so level was the smoothest at each multi-grid level. So level 1 is the finest one. And you can see mostly the computation time is spent for the level 1 smoothers. And the rest is coarser level smoothers and so conjugate gradient except multi-grid, so including sparse matrix vector multiply and communication and coarse grid solver. So improvement over the CRS is so over 40% for the sliced ELL, and 70% for the SCS-A, and so 77% for the SCS-b. And if we consider just the level 1 part, so that value is a little bit larger than this. So 50%, 95%, and 99% for each case. And so improvement over sliced ELL to the SCS is so roughly 30%. So it's so better than expectation. So this is a weak scaling up to the 1,000 nodes, so SCS-b case. And this is also the time for the MGCG. So down is good. So generally it's scalable, but you can see, especially in the case of the flat MPI, so yeah, we have a more computation time. So this is mainly because of the effect of the coarse grid solver. So this is a very well-known issue. Okay? So because the problem size of the coarse grid solver is proportional to the number of the MPI processes. So that's why we have more significant overhead by coarse grid solver. So next slide shows this fraction of the time, and the blue part is the coarse grid solver. So this is a flat MPI and hybrid 8x8. So in the case of the hybrid 8x8, it's almost scalable. Okay? Although we have a more communication overhead. But in this case, for the flat MPI, we have a very significant overhead for the coarse grid solver for the many nodes case. So this is the ratio of the improvement over the sliced ELL for the SCS-A and SCS-b case. So you can see, so the value is generally more than 20%. In this case, up is good. Okay, and although the cost of the computation in SCS-b is larger than that of the SCS-A, but generally speaking, so you can see the light color. So SCS-b is better than SCS-A. Okay, so improvement ratio decreases for the larger larger number of nodes because the sliced ELL applied to the coarse grid solver. So yeah, it's more than significant in flat MPI. So you can see, so this improvement ratio is decreasing according to the large number. So this slide shows the effect of the MC kernel, and generally, so MC kernel provides an improvement of the performance, although it's not so significant. But so it's a little bit random, and so sometimes it's rather worse. But so if you increase the number of the nodes, So the performance improvement is increasing. Okay, so I summarize my talk. So effects of the cell C sigmas are significant, and the performance improvement is 30% on Oakforest-PACS compared to the slight ELL, and good scalability up to the 1,000 1,000 nodes for various types of parallel programming models. And so MC kernel effects are also very good. So this is some future works. And so now the coarse grid solver is based on the sliced ELL. So we are switching to the cell C sigma now. And also we have many kinds of parameters, thread number, and so method for the matrix storage, and value of the C and sigma. So we are trying to develop some auto-tuning method for that. Single precision and mixed precision is also the big issues, and we have already evaluated in the preliminary work, and so yeah, it's a very expecting result. So we are also trying to extend this result to the various types of the architectures, including Intel Xeon CPUs and also A60FX. Okay, and the optimum value of the C and sigma should be larger than 8, such as 32 or 64 on the, especially in the case of the A64FX by the cell C sigma group. So we are also trying to evaluate in this type of the system. Okay, thank you very much for your attention. So I'm a general chair of the next year HPC Asia. So I'd like to looking forward to seeing all of you in Kobe next year, so in person. Thank you very much.
Thank you. So you completed your homework from last year today.
Yes, I believe so. Not
Yeah.
completely, but
okay, almost. So thank you. Since we have not so much time, but we can accept only one question if you have. So there's a question from Benson that could MPI library be improved? Benson, is it related to this talk? Could
So
MPI
yeah,
library?
earlier you had shown the flat MPI performance was not very good. You had to do some extra work. My question is, could there be something that be done in MPI?
No. So as I mentioned in this page, so these are bad performance of the flat MPI is not the communications. So this is by the coarse grid solver. So yeah, this is mainly due to the algorithm. Okay. So this doesn't matter. So MPI library doesn't matter, I think.
Thank you.
Okay. So just short question. So you mentioned that C and sigma is both 8 in this study, but is it related to the SIMD vector length like an ABX512 or?
Yes. So yeah, I forgot to mention about that. So because it's a double precision, and 64 by 8 is equal to 512. So it's equal to the SIMD size.
But then since the A64FX also has the same 512 bit in the implementation, but I'm curious why it's better to increase that more.
Yeah. So actually, it also strongly depends on the number of the non-zero of diagonals.
Yes, of course.
And so in this case, this is relatively small. It's only it's a 7-point stencil, and we have only 6 neighbors. And if we have more neighbors, I mean more complicated stencil, so we may have a very nice result for the smaller number of sheets. Yeah, I heard that. So this is just under investigation. So we are also trying to measure the values by profiler. So yeah, we have not solved that problem, but so we just observed that type of the phenomena.
Okay, thank you very much. So